In today's lab, we will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. After recording the object's motion using Tracker, we will construct computational models using Newton's second law and the energy principle. These models are created based on the assumption that the total net force is solely equal to the force due to the gravity and the force due to the spring. The purpose of this experiment is to compare the predicted versus observed motion of the data over time, and to 1. See which model best fits the data, and 2. Verify that the system follows the energy principle, which states that the total energy of an isolated system cannot change. I concluded that the models follow the energy principle and that the computational model created based on the oscillations of the x position is most accurate to the observed data. That said, however, all models become progressively less accurate over time, which suggests that another force is acting on the object that was not accounted for. After calibrating my length scale and setting my coordinate axis, I was able to record the position data of the observed object. The data was saved to a CSV file and will later be used to compare the predicted motion. Now on to creating the computer models. I created the models on the assumption that the total net force is equal to the force of the gravity and the force of the spring. The gravity force was constant, but the spring force had to be recalculated every time using iterations because it changed depending on the position and stretch of the spring. To calculate the spring force, it is necessary to know the spring stiffness K, K sub S, and relaxed length LO. The spring stiffness can be calculated using the mass in the period, which can be determined by using the graphs on Tracker. There are two possible values for the period because there are two oscillations, that in the x direction and that in the y direction. Once the period is determined, we can use the equation period equals 2 pi multiplied by the square root of the mass over the spring constant to solve for the spring constant. Afterwards, we must use the fundamental principle, aka Newton's second law, in order to derive an equation that solves for the relaxed length of the spring. When the object is at rest in static equilibrium, the net force is equal to 0. Thus, the magnitude of the gravity force is equal to that of the spring force, which is the spring constant multiplied by the difference in the stretched and relaxed length. Using Newton seconds, we can derive this third equation we will now use to solve for the relaxed length. Now onto the calculations. I determined the period for the oscillations in the x and y directions by taking the average of 3 periods, which is noted from peak to peak in both graphs. Using 3 equations outlined at the top, I calculated 2 different spring constants and relaxed lengths using these periods. We will soon see how these variations in values will compare side by side. In order to more easily compare these two models with that of the observed motion on Tracker, I'm going to insert the position data from Tracker into VPython using the CSV file I saved earlier and uncommenting certain lines of the starter program. Now that we've included the position data from Tracker, we can compare the results of the two models. The blue line represents the predicted motion created through VPython, and the red line, which is the same in both graphs, represents the observed position data extracted from Tracker. As you can see, the computational model, which calculates the period using the oscillations in the x direction, is slightly more accurate than that calculated using oscillations in the y direction. That said, it's important to note that the predicted motions in both graphs are slightly more inaccurate as time progresses. Here's the actual computer model when using the oscillations in the x direction, as we determined the more accurate model. The black arrow, which represents the force due to gravity, is constant in magnitude, but the blue arrow, which represents the spring force, changes as time at each time step. Now that we've seen the predicted motion through the computer model and how it compares to the observed motion on Tracker, we must note potential reasons for discrepancies. As we can see from the graph, the observed motion is of slightly lower amplitude than the predicted motion. This is because, or could be because, it is difficult to note the exact center of mass at each time frame on Tracker, which could have skewed determining the period for the computational model. Additionally, there could have been other forces, such as a drag force, present, which could have opposed the motion of the object in real life, and thus slowed it down. Another way of explaining discrepancies is using the energy principle, which again states that the total energy in an isolated system is equal to 0. Using the system in this instance as a mass, spring, and the Earth, we can calculate the change in total energy. Change in the total energy is equal to the change in kinetic energy and the change in potential energy, which is more specifically the change in gravitational potential energy and the change in spring potential energy. We can calculate and graph the changes in the energies using VPython. The spring potential energy and the gravitational potential energy, noted as the green and red lines, are both opposite in phase. As the spring potential energy increases, the gravitational potential energy decreases. In regards to changes in kinetic energy, noted as the blue line, the mass gains and loses kinetic energy and oscillates twice as fast as the potential energy changes. Finally, and most importantly, keep note that the change in total energy, noted as the yellow line, is zero. Because the change in total energy is zero, we can say that the model does indeed satisfy the energy principle. Now, it's important to note that this is a simplified version of the energy principle, which assumes that no energy is transferred to and from the surroundings of the system. In actuality, the energy principle also takes into consideration the change in thermal energy. As energy is transferred between potential and kinetic energy as the mass moves, some of it is transferred as heat, aka thermal energy, which we do not account for and thus may also be a cause for discrepancy in the data. Finally, let us do one last quick overview of differences in the model created by the oscillations in the x and y direction. We can see that the two models have similar amplitude, but the main difference is that the oscillations in the y direction become significantly more inaccurate over time in comparison to that of the x direction. This can be due to the inaccuracies in plotting the center of the mass and tracker, as well as our disregard of the energy lost as heat, as we looked at through the energy principle. That's all for today. Hope you've gained a better understanding of how the energy principle can be observed in everyday motions.